So in two dimension, we basically define the scalar product of two vectors, also called the dot product, to be equal to magnitude of u times magnitude of v times the cosine theta, where theta is the angle between two vectors. Well, this is exactly also valid in 3D, so that doesn't change. And so there are two consequences of that. Consequence number one is that if u perpendicular to v, well, that means that theta is equal to 90 degrees, so u dot v is equal to 0. That's second consequence of that is that if we do u dot u, so the dot product of a vector by itself, that's u dot magnitude of u times magnitude of u times cosine 0, which is 1, so therefore it's u square. And if this vector happen to be a unit vector, which means that this length is equal to 1, then u dot u is equal to 1. Okay. Now, like in 2D, there are three properties of the dot product, and the first one is commutativity, which means that u dot v is equal to v dot u. We can commute the vectors. The second one is associativity, which means that k times u dot v, where k is a real number, is equal to k times u dot v. And then the third one is distributivity, which means that u dot v plus w, where w is another vector, is equal to u dot v plus u dot w. In other words, we distribute like we would have done with the normal multiplying operation for scalars. Now, these three properties, they are demonstrated exactly like in 2D, so therefore I'm not going to do it. Now, in 2D, if we have a vector u which has for components u of x and u of y, and then another vector v which has for components v of x and v of y, then u dot v is equal to ux vx plus uy vy. This was demonstrated in 2D. Now in 3D it's not much different. In 3D, if we have u which has for component u of x, u of y, u of z, and v for component v of x, v of y, v of z, well, guess what? The dot product of u of v is equal to u of x, v of x, plus u of y, v of y, plus u of z, v of z. And this I'm going to demonstrate. It's not difficult. Well, so say u dot v is equal to u dot vxi plus vyj Now we are going to use the distributivity, but because I've done the distributive only with two vectors, I'm just going to rewrite it a bit differently so you are not saying, well, Philip, you're not demonstrating you're not using the things that you have demonstrated exactly. So here we've got two vectors. We've got this vector, vector1, and then we've got another vector here. Okay, so now I can use the distributivity. So it's equal to u dot v of x I plus v of y j plus u dot v of z k. Okay, so it's equal to, I'm using the distributivity again for this part. So that becomes u dot v of x I plus u dot v of y j. And then here for the second part, I'm using the associativity. So it becomes v of z times u dot k. And here, okay, so I keep on going. So here I use the associativity, so that's u times u dot I plus v of y times u dot j plus, and this one, that's v of z, and I'm going to replace u by its component, so it's a uxi plus uyj plus uzk. Okay, so now I'm going to try to go a bit faster because I'm running out a bit of room. So that's u times u of x I plus uy j plus uzk dot I plus vy times uxi plus uyj plus uzk plus vz hang on, oh, I missed the k here, dot k ux vz I dot k plus vz uy I, sorry, j dot k plus vz uz k dot k. Now this one is equal to 0, this one is equal to 0 because I and k are perpendicular, j and k are perpendicular, so the only one that's left is this one. Okay, well, with the same principle, you can see that here, basically the only components left is going to be v of x, u of x, because when I distribute this j dot I is going to be equal to 0, and k dot I is also equal to 0, and then forgot a j here. So again, using the same principle, I dot j is going to be equal to 0. This one is not going to be equal to 0, and this one is going to be equal to 0. So what is left is vy uy plus vz uz. And here we go. That's proven. Okay. So application of this. So the outcome is that basically u dot v can be calculated in two ways, which is, well, the definition, amplitude of u times amplitude of v times cosine theta. And if we know the component, it also could be u of x v of x plus u of y v of y plus u of z v of z. application. So that means that cosine theta, if we don't know the angle between two angles, is equal to ux vx plus uy vy plus uz vz over the amplitude of u times the amplitude of v. So for example, if we have two vectors which are, say for example, u is equal to 2I minus j plus 3k, and then we have the vector v which is equal to I plus 2j minus k. Well, what is the angle between these two vectors? Well, it's equal to cosine theta, which is at, well, so we times this one by this one, so that's 2 times 1. And then this one by this one, so that's minus 1 times 2. And then this one times this one, so that's 3 times minus 1. Okay, and then for the amplitude, well, the amplitude of vector u is equal to 2 square plus 1 square plus 3 square, and the amplitude of vector v is equal to 1 square plus 2 square plus 1 square. Okay, so that's what? A bit of simplification here. Minus 3 over, what do we have? 4 plus 1, 5. 5 and 9, 14. So root of 14 times root of that 4, 6, 6. And then from there, well, using, so therefore theta is equal to, well, you use cosine minus 1 of this thing. Here we go, and you find theta. Yes, that's it.